All right, let's do this thing. Okay, good. So last time we proved the difficult half of Katok entropy rigidity. So I'll just remind you what we proved last time. Got a variable negative curvature surface, compact. I'm always assuming compact. I'm just not saying it. And the Lugol entropy, so the measured theoretic entropy with respect to the natural kind of volume type measure, is maximized at the constant negative curvature metric, and you only get equality at the constant negative curvature metric. So this entropy can tell if you're constant negative curvature or not. So what I want to do today, and this is actually way easier, is the other half of Katok entropy rigidity. So today we're going to prove a theorem. Okay, so we're going to do a closed Riemannian surface as usual. And what I'm going to assume this time is that G0 equals rho. Okay, so I'm going to assume, so I'm assuming that the G can be written as, sorry, I'll just write the statement. So this is what I'm assuming: G0 equals rho times G, where G0 has constant negative curvature. So, and remember, this is yeah, always happens when genus is greater than or equal to 2 by the uniformization theorem, right? But I just wanted to set up my notation as I'm going. Okay, so I'm assuming I'm on a surface with genus at least 2. That means I'm conformally equivalent to a constant negative curvature metric. And I'm also going to assume that, that this is chosen so that the area of G is the same as the area of G0. Of course, this is just bookkeeping. I can just rescale to make that true. Okay, then the topological entropy G is greater than or equal to the topological entropy of G0, and of course this one equals that same thing I got up there, minus 2 pi chi m over v g equals vg0 to the 1/2. Okay. And with equality, how should I write it? And only if rho equals 1, i.e., again, you only actually get there at the constant curvature case. Okay. So yeah, this is kind of amazing. So i.e., G goes to H top G is minimized constant negative curvature. Okay. So that's what we'll prove. Obviously, contrasting with the previous one, the Lugol entropy was maximized at constant negative curvature. And of course, at constant negative curvature, those two entropies agree. So I'll give you a slogan for why this is true in a moment. But let's look at the consequence of this, and this is the real kind of rigidity aspects of it. Oh, also notice that my hypotheses were weaker here. So in the in the first thing, both the constant negative curvature guy and the things I was varying through, I needed a negative curvature assumption to make everything work. This is actually more general. So G here can be that there's no assumption on it at all other than that. It's on a surface which supports a constant negative curvature manifold metric. Okay, so this could have some bumps of positive curvature. So this is actually, in this statement, we got a weaker assumption on G. But anyway, if we restrict to the negative curvature guys, oops. So among the negative curvature metrics, with a fixed area, then this is giving us that the Liouville entropy equals the topological entropy if and only if G has constant negative curvature. Right. This is the number we get at constant negative curvature. It's an upper bound for this number and a lower bound for this number. So they only match up at constant negative curvature. Okay, so the entropies only match at constant negative curvature, and what does that do for us? In particular, so two measures with different entropies cannot be the same. So in particular, the Bohm-Margulis measure, i.e. the measure of maximal entropy, the unique measure whose entropy is equal to that number, equals the Liouville entropy, sorry, the Liouville measure. So the Bohm-Margulis measure and the Liouville measure are the same if and only if G has a constant negative curvature. Right, so this is like the important kind of rigidity that comes out of this, and that this last statement has moved away from entropy. Entropy was just, if you think of entropy as just being a tool, you got maybe the measures themselves are more fundamental than the entropies. You've got this Liouville measure that's obviously important. It's coming from the Riemannian structure. Hopefully, if you do dynamics or you've been on this course, you also believe that the Bohm-Margulis measure, aka measure of maximal entropy, is important. You want to know if they're the same thing. Well, if they are the same thing, then that's a very, very strong and special thing. It means you're at constant negative curvature. Okay, it's an if and only if. Yeah, so that's the payoff from all this stuff. This is Katok entropy rigidity. Okay, I should have probably, let me just double down. I mean, I think that these assumptions are upstream here, but this is, okay, no, I guess the word area was also suggestive, but this is for surfaces, right? Okay, so there's something called the Katok entropy rigidity conjecture, and that says that you want the same statement to be true, replacing the word surface with manifold, and that is a major open problem. That's serious business. Maybe at the end of this lecture, I'll start saying what's known towards that. There are some things known towards that, but you would like to say that for manifolds, so you would like to say that among negative curvature manifolds, that you only get these two measures matching up. Well, not quite a constant negative curvature. For those of you who are into this, the correct replacement for this in higher dimensions is locally symmetric. There's like because you have more dimensions. There's like, yeah, anyway. But basically, you know, these things should only match up if you're on a small collection of well understood kind of model spaces, and as soon as you've got kind of varying curvature, you expect these two notions to differ. Let me give you a slogan for why this is true, counteracting. I think I can sell this a bit more than the Liouville entropy phenomenon. I mean, the only slogan I have for that is that the Liouville measure is dumb. And somehow it just sees what it sees, and as soon as you got some varying curvature, you know, it's just inefficient, and it just doesn't see some of the complexity and just kind of wastes some complexity. That's the best slogan I could come up with for that. But I think really, you know, the opposite side of that is maybe a little easier to believe here. Okay, so what's the counterpart to that? Well, topological entropy is kind of smart, right? It's, you know, it's a supremum of all your complexity. So let's think about what happens here. So entropy is, you know, it's measuring how many orbits you have, how much complexity you have. And what gives us more entropy is, in this context, you know, things being spread out faster, things being contracted faster, everything going faster. And in this setting, that's going to come from stronger negative curvature. Stronger negative curvature being more negative, right? Curvature negative 1 million, and that's going to be super strong negative curvature. That's going to be spreading things out faster. That's going to give you more closed geodesics. So think about constant curvature. You know, but because the topological things, you know, if you scale downwards, your curvature goes up. So think about a tiny hyperbolic thing, right? Just think about your constant curvature negative one thing, and then just scale that thing down. And that's going to make its curvature get stronger and stronger. More things are kind of, you know, everything's just, you know, or conversely blow it up and it gets kind of weaker and weaker, and things take longer and longer to spread out, just because, you know, if you multiply that thing by times 1 million, you know, it's like, you know, it's like the Earth, right? You don't see the curvature where you're standing. Everything's just so big and spread out. Anyway, so yeah, so in this setting, we're going to have some patches of, you know, more negative than average, some patches of less negative than average, and somehow we're going to see geodesics spreading apart faster in the more negative than average regions. And what I would say here for this slogan is that, you know, the entropy has the luxury of kind of zooming in on, you know, the most complexity. You know, it's kind of built as a supremum. You know, if you think about, you know, what this measure is seeing, it's going to kind of want to see that it's going to want to give more mass to the regions with the most complexity. That's how it's going to kind of see. That's how it's going to maximize that entropy. So I would say that the phenomenon here is that, you know, as soon as the curvature varies, if you start thinking about, you know, defining this guy, taking a supremum over all the measures, as soon as it varies, there's going to be some wiggle room for this guy to zoom in on those regions of stronger than average negative curvature. That's what it's going to want to do to maximize the entropy. So I would say that's why it's a rigidity result. You know, as soon as there's that wiggle, you know, the entropy is going to detect that and use that to its advantage and give more mass to the region of greater complexity. So, you know, the entropy is going to bump up relative to this guy, and the two measures are going to be different. I mean, we'll see an actual proof in a moment, but which will not go like what I just described. But I don't know. Anyone buy that philosophy? I think I buy that philosophy, but maybe I didn't explain it very well. Yeah. Okay. All right, let's prove it. Okay, so what's our setup? It suffices to show that the entropy of G is greater than, yeah, I'll just write H's from now on, I think. No, that's just pointless extra notation. H top of G is greater than or equal to H top of G0. Where G0 equals rho G and VG0, so the area, total area or volume is G0, G0, constant negative curvature. I probably had all of this in the statement, but just for emphasis, let's write it out again. Okay, so this is what we're trying to show. So we've had to normalize the area. I mean, this is what I was hinting at earlier. Of course, if you rescale the whole thing, entropy changes, right? It's just like uniformly speeding up or slowing down the whole thing. If I take a fixed m, blow the whole thing up by scale 1000, right? We got exactly the same thing, but it's just we've just kind of slowed everything down by the same factor everywhere. But entropy changes because we're counting everything up to length t, and we've got a different length t once we've rescaled. So yeah, these statements only make sense once we've normalized area. Okay, so fix a large t. I want to fix a large t, probably. We'll see how we go, and consider the periodic orbits, aka closed geodesics for G0 t. So that's all the ones with length up to t. And I'm not going to fix a large t. I'm going to say for large t, consider this, right? Okay, so we know, again, what we did earlier, of course, we know that if we look at the growth rate of this guy, we're getting topological entropy of G0. So again, periodic orbits are going to be a key actor here. And we also know that mu sub L G0, so the Liouville measure for G0 is the unique measure of maximal entropy for the geodesic flow with respect to G0. Right, this is only true, well, as we'll see, this is only true at G0. Let's just think a moment, why is it true for G0? There's probably various ways to see it. I would go back to that homogeneous measure stuff that we saw right at the beginning. Constant negative curvature, everything looks the same everywhere. You've got lots of nice hyperbolic structure. And observe that this is a homogeneous, that mu-L is a homogeneous measure per the definition from 5 or 6 weeks ago, and that will show that it's the measure of maximal entropy. I'm sure there's other ways through too, but that's the first thing that comes to my mind. Okay, so we know that, okay, so that the Liouville measure is doing double duty for G0 is Liouville and MME. And okay, I guess we're also using the closed geodesics equidistribute. Yes, we are using that. Okay, so for continuous f, no, let's say I guess. So for continuous function, let epsilon be greater than 0, and define per t epsilon phi to be the set of periodic orbits such that the difference between, notation shall I use? Sorry, I've been indecisive on notation in this lecture. How should I write it? I know, I'll write it as integral of the observable d mu gamma. So that's going to be the natural measure on the closed geodesic. I'll write that in a second. Over the length of gamma, G zeros everywhere, just to be clear, minus the integral phi mu L, G0, that is less than epsilon. Okay, so we're going to look at all the individual closed geodesics such that you average the observable on the geodesic, and what you get is close to the integral with respect to Liouville. So of course, but by the ergodic theorem, almost every point, you're going to get this convergence. But we're not doing almost every here. This is the actual, this is the countable set of closed geodesics, right? So this is a different statement. So it's getting an ergodic theorem almost everywhere type results, but we want to get it on the geodesics. So there's a little trick for that, which I'll show you in a minute. Okay, so by this, what I mean here is just what you think it means. Just integrate. I mean, notation, but just integrate this thing. Along the orbit, right? So it's just evaluate. It's a closed orbit. Just evaluate the function along it. So it's like a sum. Just normalize it by length, so it's like the average, right? Okay. So the claim is that the number of periodic orbits in this set, which are kind of almost typical, divided by the total number of orbits, converges to 1 as t goes to infinity. I'm just going to do a sketch proof. Well, okay, this is going to be a short proof, but I've got a big machine in the background, which is pretty cool. It's another advertisement for some abstract thermodynamic formalism. So I'll explain in a second. So if not, there are enough, and by enough I mean greater than or equal to some epsilon 0 times cardinality of per t gamma v not in per t epsilon phi to construct an MME, which I'll label M. Okay, let me explain in words a little more. So assume that this is not true, okay? So I do not get kind of a full proportion of these objects being in this set. If this is not true, then there's a definite proportion of these, which do not satisfy this, right? And because there's this positive proportion, this is going to give me, I can use periodic orbits to give me T epsilon separated sets. So if I have this many periodic orbits where this fails, think back to building MME. We've used this trick a few times. I can put that data in there, and I can take a limit measure of, as we've seen before, of built out of all the objects in the complement of this guy. I'm going to get a definite growth rate. The limiting measure is going to be a measure of maximal entropy. By construction, the integral of the function with this constructed guy is different from the integral with respect to the Liouville measure, right? Because this function is definitely integrates definitely away from this guy, right? Okay, so like I said, this is a couple of lines of proof, but there's a big black box that we're about to hit it with by the uniqueness of the measure of maximal entropy. This is a contradiction. Okay. So here's a nice little place where that big abstract uniqueness of measures of maximal entropy proof for hyperbolic flows just came up. And remember, that's a serious proof, taking several lectures and got quite a bit of theory. Okay. And in a completely general setting, I mean, we're all comfortable with the Ergodic theorem, but how do you get from an ergodic theorem type statement for almost every point to something, on this countable set? I mean, I don't know. I mean, most times it wouldn't be true, right? So, there's something, we've really used all of our theory to get this statement, to get this typical behavior on, like a full proportion of the periodics. Okay. Any questions about this? Okay, so this is a nice trick. This can be used in various other places too. But we've got for, a full proportion of the periodic orbits, the averages of a function along the orbit come very close to the Liouville measure. Okay, so again, we've reduced the periodic orbits. This is a very kind of typical trick. Okay. Okay, so now assume that T is large enough so that the number of points in T epsilon rho to the -1/2 is greater than 1 minus epsilon times per t. Okay. And the row here is the, I'm going to write it again. This is always going to be that conformal factor, the function, so that g0 equals rho times g. We'll see why this is the relevant thing in a moment, particularly why it's exponent minus 1/2. Okay. I'm going to look at periodic orbits, whose typical behavior is telling us something typical about this relevant function here. Okay. Okay, so a couple of things to recall. Note that the integral over the unit tangent bundle with respect to g0, rho to the minus 1/2 d mu L g0 equals the integral over m, rho to the minus 1/2 dm g0. We saw that a couple of lectures ago, right? Remember, this is on the unit tangent bundle, but yeah, but because this only depends on the base point and not the direction, just kind of integrate around the circle, and we can just integrate this on m instead of the unit tangent bundle. And m is just at the normalized, m's normalized volume. Which equals m rho to the 1/2 dm g. Okay. Again, we saw a couple of lectures ago how you can get from there to there. Which equals g comma g, this bracket thing, g0, right? And if you want to look back to believe all of these things, this was all in lecture 28. This last one was lemma 1 from that lecture. Okay, and also note that the length with respect to g of gamma, okay, so, you know, let's just think back to undergraduate lengths of curves, right? Calculus things, right? I mean, what's the length of the curve? Parameterize it, and you kind of integrate along the curve of the derivative of your parameterization. That's the length of the curve, and of course you can parameterize it as many ways as you want, so it's all fine. Of course, usually we parameterize it by arc length, and maybe we forget the original definition because most of the time we just do the obvious definition. But okay, I'm going to parameterize this. So I'm thinking about g length, but I'm going to somehow give this its kind of g0 parameterization. So I could compute this by parameterizing it according to the g0 geodesic flow, and I'd be integrating up to the length with respect to g0 of fs g0 gamma dot 0 g ds, right? So I've just parameterized this according to what's going on with g0, but integrating the g norm, right? Because that's the relevant thing. Which equals the integral of square root of rho inverse g0 of what's in here, which equals integral 0 up to LG0 of gamma of rho to the minus 1/2 ds. Okay. So if I want to compute the g length, I can integrate, from 0 up to the what is g0 length would be of this conformal factor, the -1/2 in there. Okay. And again, but where am I going here? We're comparing. What am I trying to do here? I'm trying to compare G entropy to G0 entropy. So, I'm looking at growth rates of periodic orbits up to length t with respect to the two different metrics. So I want a comparison between G0 lengths and G lengths of closed periodic orbits so that I can compare those two numbers. I was just doing a little bit of prep work for that. Okay, so we have that the LG length of a curve is therefore the LG0 length of a curve times the average of rho to the -1/2 along gamma. I'm just writing it like that just to be suggestive. So I got to here. To make this an average, I can divide through by that length. I can divide through by LG0 gamma to make it an average. And then, of course, I get a spare LG0 gamma term there. Okay, so for a curve belonging to per t epsilon rho to the -1/2, then what do we get? We get LG gamma is less than or equal to t. Right, the t is coming because okay, so this term here, thing went in there with G0 length less than or equal to t, and then the second term is G0 epsilon. Right, and that's coming from here. Average of this thing. There it is. Equals that. Right, the point was that these things, the integral along the curve, the average along the curve is within epsilon of the integral with respect to Liouville. Right, that's that equals that. So we get this. You can look this over later if I'm jumping around too much. But the whole point was the average along this curve is within epsilon, the Liouville measure integral of this guy. So that gives us that number, well, within epsilon of that number, so within epsilon of this number. This is a great proof. Katok, he's the guy. Good, that was the analysis bit. Now what we see a trick we saw last time. Place each such gamma by the G shortest curve in its homotopy class. So remember we talked about this last time, it's important, so it's worth saying again. So gamma was a closed geodesic as far as G0 was concerned. Now we change our glasses, we're looking at it from the point of view of G. Now it's just a closed curve. It's no longer a closed geodesic, but it's in a homotopy class. That is, it has its kind of, the path it takes through the topology, but we can pull it tight. The shortest curve, as far as G is concerned, the shortest curve in that homotopy class is a closed geodesic. So we take gamma, which at this moment is a closed curve, but not geodesic for G, but kind of pull it tight. That's going to give us a closed geodesic for G, and shorter than gamma. Okay, so what have we done for each gamma? We just created something which is a G closed geodesic whose length is upper bounded by this. We've shown that the number of points G closed geodesics with length up to G, yeah. So every gamma that we did this procedure with gave us a G closed geodesic with length bounded above but by this number, right? So we were starting off with T closed geodesics, yeah, G0 closed geodesics with length up to T, and I'm building G closed geodesics with length up to this. Each different thing I put in here gives me a different thing out here. And how many of them have I got? Well, I was building different ones for different things I was inputting. So the amount I just built was bigger than the number of G0 closed geodesics, which kind of looked like rho minus 1/2. And as we saw, we have lots of these. Positive proportion of the uniformly positive proportion of these. So we just built lots of them. Take a logarithm and normalize. It follows that H star G. Right, take a log, divide by this number, take a limit. It's greater than or equal to G0 minus 1. H star G0. The epsilon was arbitrary, so that's coming out in the wash. But once we divide through, the G0, it's going to stay on both sides. Okay. I'm writing out less details this time than I was in the last couple of classes. Yeah. Okay, and again, we know something. Oops. What do we know about this number? So it goes back to that thing we did in lecture 28. Right. So thus H star G is greater than or equal to H star G0 with equality if and only if rho equals 1. Pretty cool, huh? Thanks. Yeah. And Katok was a very, very, very clever guy. Yeah. Yeah. Okay. Party. Yeah. Right. Good. Any questions? All right, we did it. We proved Katok entropy rigidity for surfaces. And you know, I think that this is something that I really wanted to focus on this semester. This isn't in any textbooks. Maybe it should be. It's not so bad a proof. It's, once you set everything up right, it's a very elegant proof. To my knowledge, it's never made it into a textbook. So this is beyond textbook stuff. And a really nice thing about it is it uses so many of those kind of basic, or basic in the best sense, ingredients of this kind of area of hyperbolic dynamics and geometry. You know, all those tools we were building up all semester, you know, actually the majority of things we were building up all semester went into this. We needed some thermodynamic formalism, abstract thermodynamic important way. You know, there was some nice tricks with the Ergodic theorem. All those characterizations in terms of periodic orbits were absolutely key. All that came together and gives us this nice elegant proof, you know, which tells us really, you know, forget about, you know, we can decide to just care about entropy. I certainly am convinced by just caring about entropy. But if you decide to be an entropy skeptic, you know, you can get a conclusion which has nothing to do with the entropy theory, and, you know, just care about, well, okay, I guess implicitly the entropy theory is built in there. But, you know, you got a statement which is kind of external to things about these numbers. It's about different important measures, whether they coincide or not. So, and can dynamics identify the geometric fact of constant curvature? And the answer in this sense is yes. So that's pretty cool. Okay, in the remaining couple of minutes, let me just say something about what else is known. Okay, so high dimensions. Okay, so there's famous work by Besson. Oh, I didn't check the spellings. I hope there's a correct Besson, Courtois, and Gallo. They showed that H top G is minimized at constant negative curvature in all dimensions. So this was you know, famous work in the 90s. This was a real high water point of 90s dynamics. It's a different proof. It's way harder in higher dimensions. I stated it like this: that this is true as stated. What they actually show is minimized at you know, negative curvature, locally symmetric spaces. So in high dimensions, if you quotient some of the more exotic model spaces, you get homogeneous spaces which have curvatures -1 in some directions, -4 in some other directions. It's complex hyperbolic things, quotients. Anyway, let's not worry about that too much if you're not into it. But yes, so this did generalize. Let me also mention what are the names? Okay, I'm blanking. One of the two co-authors was Benson Farb. They also extended this to Besson, Courtois, Gallo to manifolds with cusps. So this is a really robust thing, but it needs really different techniques to get beyond surfaces. Now I'm just going to write mu L goes to H mu L. It is a mystery in high dimensions. Okay. Definitely not maximize a constant curvature. And that was a result by Flaminio. So he came up with an example of a 3-manifold, and he just did local analysis, just studying the derivative of this functional at a particular 3-manifold. He could show that the derivative had mixed signs, and therefore not a minimum. And that uses like some really heavy tools of algebraic tools available in that setting. He's analyzing like the Casimir operator and doing representation theory, and I don't know, it's a whole thing. It's interesting. It's hard for me. But that isn't to say that the functional sorry, what am I writing here? I think you all knew what I was going to write. I just botched it. Okay. But G goes to H top G minus H mu L G. I mean, that's the big question, right? There's no reason that it might be true. In fact, it's conjectured. Katok entropy conjecture. It says that H top G equals H mu L G if and only if G is locally symmetric, i.e. constant negative curvature or one of these other slightly more exotic spaces. And this is open and this is one of those big open problems, right? So this is still serious stuff beyond the surface case. I'll just mention one more result and I'll stop. There's interesting work by Foulon. What does he prove? Goodness, should have checked. Okay, I'll just say the setting. Extension of Katok. I can't remember whether he gets the whole thing or just the Besson-Courtois-Galop part to 3-dimensional contacts and also flows, whatever they are. I won't tell you quite what that is, but the 3 dimensions is key. And this is something that generalizes negative curvature geodesic flows. So that's another direction this was generalized, and there's still some questions there. So yeah. So we have a beautiful theorem in the negative curvature surface case, and a whole bunch of mysteries in settings beyond that. Any questions? Oh, thanks for the link, James. Did you see that ludicrous display last night? All right. Very cool. So we just got to a really good place to be at in the course. We just proved really that the main thing that I wanted to prove. discussed it a little bit. Going to stop the recording.